Alright, welcome back. So this is continuing on extensions of hyperfields, and this section we will be going over section 3 on the first main theorem for constructing hyperfield extensions for quotient hyperfields. So let's set some terminology. I will let F be a field. I will let G be a multiplicative subgroup of the multiplicative group of F. I'll let K be F mod G is the quotient hyperfield. And I will let K of T be a polynomial over my hyperfield that contains no roots in my hyperfield K. And our goal of this section is, our goal is to construct a hyperfield extension L. So we will construct a strong extension L over K such that our polynomial little k has a root in L. Alright, so first things first, we will need a lemma. So if you recall at the end of the last section, we kind of talked about what polynomials over a hyperfield are. And we kind of said, well, if I have a quotient hyperfield and a polynomial over the field, there's an induced polynomial over the quotient. So this lemma can be kind of thought of in the reverse, or, well, we kind of want to do this in reverse. And to say, we're going to start off with our polynomial over our hyperfield, and we want to lift it to a polynomial over a field. So this is the first step. So if I have f is a polynomial over my field, so I use x for variables over the field and capital T for variables over the hyperfield. And let's just say f of x is the sum of ai x to the I. Then, if I take some element, call it gamma in f, if f of gamma is equal to alpha, then when I look at sort of this induced setting, if I look at my polynomial over my hyperfield, we have that the equivalence class of alpha will belong to the set of plugging in the equivalence class of gamma into the induced polynomial. So we will now prove this. So the proof, we want to show that alpha is in the induced polynomial applied to gamma. So if we recall, the induced polynomial applied to gamma is the hypersummation from 0 to infinity. Well, my polynomial was this ai, so my induced polynomial will have the equivalence classes of ai's. And instead of x or gamma to the I, I'm going to plug in the equivalence class of gamma to the I. But really, this will be the same as adding the equivalence class of ai gamma to the i's together. Kind of just using that this is a multiplication here. And that's how multiplication works for quotient hyperfields, and similarly for exponentiation. So then the observation that we make is alpha is equal to the sum from I equals 0 to n of ai gamma to the I. So we will have that alpha has to be in sort of the set sum of kind of the a sub i's gamma to the i's. And if we recall with how quotient hyperfields work, alpha, since alpha can be written as this sum, each of these elements are part of this hypersum. And this hypersum, this implies that the equivalence class of alpha is in my hypersum. So we have that alpha is in the induced polynomial acting on gamma. So alpha belonging to this sum here just is equivalent to the equivalence class of alpha being in the hypersum. And we know alpha is in this sum because alpha is, in the field sense, is written in this sum, and each of these elements are in each of these sets. So we've just shown that if f of gamma is alpha, then if I look at the induced polynomial over sort of my hyperfield, then the equivalence class of alpha is in the equivalence class of, or the induced polynomial acting on the equivalence class of gamma. And so a nice corollary to this is if I take my polynomial in my field and it has a root, then the induced polynomial in the hyperfield sense must also have a root. Or this should say has a root. And this is just apply the above lemma with, well, if f has a root, we can find some element that it's 0, so 0 is in f of some element. So we now know that if my polynomial over my field has a root, then the induced polynomial over the hyperfield has a root. So here's kind of the last lemma that we need is if I consider a polynomial over a hyperfield and this has no roots, and recall my hyperfield here, I'm assuming in this section it has this quotient structure f mod g. So everything I'm saying here is just for quotient hyperfields. So I have a polynomial that has over my hyperfield with no root. Then I can find a polynomial f over the corresponding field with no roots, such that if I look at the induced polynomial of f, this is now a polynomial over a hyperfield, it is equal to k. So this is kind of this lifting procedure that I said. If I have my polynomial over my hyperfield with no roots, I can find a polynomial over my field that also has no roots, such that when I look at the induced polynomial in the hyperfield setting, it's the same. So the proof is, well, let's say k of t. So let's say k of t is my hypersum of some equivalence classes of a sub I t to the I. This is my polynomial over k. So let's just consider the polynomial over my field now. So I have my polynomial over my hyperfield. I'm just going to consider the following polynomial over my field of ai x to the I. Kind of by construction, my induced polynomial of f is equal to k. So it just now amounts to show that little f, my polynomial over my field, has no roots. So if we do this, so assume for, and really, the AI I choose here, it doesn't really matter. This could be, you could pick any representatives for any of these. I'm just saying, pick whichever one you like. And for all of these will actually, none of these will have roots. So by construction, f bar is k, and so now we just have to show that this f has no roots. So assume for sake of contradiction that f does have a root. In f. Well, then by the corollary above, so this corollary right here, which says if f has a root, the induced polynomial over the hyperfield has a root, this implies that f bar, which is equal to k, has a root in k. But we assumed this has no roots. But we assumed little k has no roots. This is our contradiction. So we now know, given a polynomial over a hyperfield, we can kind of lift it up to a polynomial over a field, and if the polynomial over the hyperfield has no roots, then the corresponding polynomial over the field has no roots. And yeah, we are now ready to prove our main theorem. So, theorem. If little k in k adjoin t has no roots, in k, then there is a strong hyperfield extension L over k. And we're going to construct this. And so this is just in the case of, remember, everything here is just for quotient hyperfields. So here's the proof. Since little k of t has no roots in k, we can use this lemma. K has no roots, then we can find the polynomial in f with no roots. So by our lemma, we have some little f in f of x. So now we have lifted up to a polynomial over a field with no roots in f. So now, all we have to do is by classical field theory, you can consider f of x mod out by the ideal generated by f, assuming f's irreducible, or just take some irreducible part of the polynomial f and do that. So by classical field theory, there is some field extension. I call this f prime over f, such that f has a root in f prime. So I have extended my field to have a root. So now we will let L be the quotient hyperfield f prime modded out by G. Remember, K is f mod G. And if you recall from last time when we talked about strong extensions, we had this theorem up here, or this lemma. If L mod f is, if I have a extension of fields, L over f, if I take this multiplicative subgroup, then the extension of fields modded out by the same subgroup is a strong extension of the field f. So this tells me by our previous lemma, we know L is a strong extension of K. So we have our strong extension. We have constructed it. And so now we just have to show that L has a root of little k. Well, indeed. Since we have f prime has a root of little f, right? By this corollary here, if I have an element with a field, or a polynomial that has a root over the field, then the induced polynomial in the hyperfield setting also has a root. So since f prime has a root of f, this tells me that f prime mod g has a root of the induced polynomial, which is k. And this is exactly what we wanted. We have constructed our strong extension L that has a root to this polynomial k, where k had no roots to begin with. And this is a strong extension, which, since strong extensions are also weak, so this is the best we can ask for. Well, this isn't the best we can ask for, because here is, perhaps I'll do the open problem first. The question that we have is, can this be done for general hyperfields? So I have only answered the question for quotient hyperfields, kind of exploiting classical field theory. But the problem still remains open for non-quotient hyperfields, or general hyperfields. However, you would expect it to be true. So maybe I will give an example of this theorem in action, and this is kind of the theorem, the example that motivated this. So I talked about the phase hyperfield. So consider the polynomial 1 plus t squared over the hyperfield of sines. And let's recall the hyperfield of signs has sort of this quotient structure of r modded out by the positives. This has no roots because whatever I plug in for t, if t is negative, positive, or 0, well, when I square it, it'll either be positive or 0, and if I add something positive, plugging anything into this polynomial over the hyperfield will just return 1. So this has no roots. And so sort of the lifting structure says, so this implies, so when we lift, we get 1 plus x squared in r bracket x has no roots. And I should remark, this 1 plus x squared, this isn't unique. I could have taken, if I replaced 1 with any positive number, and if I multiplied x squared by any positive number, this still doesn't have any roots, because no matter what you plug in, it's still going to be positive. But this is probably the simplest and most common representative you would take. And so our construction says, well, what's an extension of r that has a root to 1 plus x squared? Why, that's the complex numbers. So C is the extension of R. And so we have our phase hyperfield, which is C modded out by the positive reals, is our extension of the hyperfield of signs. And we saw this was an extension last time. And so this was kind of the motivating example behind doing this construction in this way. And I might remark, if we kind of go up to our picture of the hyperfield of signs, we can actually see our roots to this polynomial, because if it's just going to be whatever the equivalence class of I is, because when you square that, you get the -1's equivalence class. And then when you add that to 1, you'll have 0. But you also have minus I is also a solution. So we do have roots in the phase hyperfield, coming from whatever the equivalence classes of 1 and I are. And so that is the main construction and the first of the 2 theorems of this. All right, thanks for watching.